Hello and welcome to a re-recording of some video lecture material that was lost due to the recording software crashing. This is a overview of thermodynamics that I didn't cover in a lecture last year. It was material that I thought everyone would be familiar with, but as the class went on, I realized that it was some material that needed to be covered. So this year I included it directly into the lecture rather than getting it a little bit at a time as sort of asides throughout the course. The rest of the material that was lost in the crash was covered. So I'm going to put a link to last year's lectures up on Carmen for you guys, so you can see the rest of the material, and then this thermodynamic section will be its sort of own standard. And so, right, we talked about how in aluminum alloys, the choices for alloying elements are pretty low because of the low solubilities of a lot of systems, a lot of elements, except for our major alloying ones, such as copper, lithium, magnesium. Right, silver has a lot of solubility, but we don't exactly use aluminum silver alloys for anything, and zinc. Right, and the consequences of those low solubilities is that we don't have a lot of choices for alloying, and many elements, even at impurity levels, are going to lead to secondary phase formation in intermetallics. But it also means that we can make advantage of this secondary phase formation by developing a fine dispersion of these secondary phase particles, and that's going to be a prime alloy design strategy for a lot of for many aluminum systems. And here we can see a very fine dispersion of theta double prime particles. This is this metastable phase here that we'll talk about in great detail later in an aluminum copper alloy system. So if we want to talk about how we can develop this fine secondary phase dispersion that's going to give us good strengthening, we need to go back and do some thermodynamics. And if you remember, when I talked about my rules of thumb, of how I think about the metallurgical world, I discussed the common tangent construction and how useful it was. So we're going to have a review of that. And we need to then talk about how nucleation actually occurs. Right? So let's go back and let's start with our definition of Gibbs free energy. Right here we have the change in Gibbs free energy is our enthalpy, change in enthalpy minus T temperature times the change in entropy, right? So this is just sort of the fundamental definition of Gibbs free energy. And we have to remember a couple obvious things is that when for a change to be happening at reversibly or at thermodynamic equilibrium, it means that the change in Gibbs free energy has to be equal to 0. Right? And so let's take a look at what happens when we make a solution. We're going to have a binary solution between two metals, between two elements, and we're going to take a look at regular solution theory. Regular solution theory was also another one of my rules of thumb that allows me to think about metallurgical things in a sort of a coherent and consistent consistent manner. And regular solution theory basically just says that the entropy of mixing excuse me, follows that of an ideal solution, right? So this is just nothing but our entropy of mixing from an ideal solid solution. It's just the superposition of microstates, the number of potential microstates of the system. But we say that the enthalpy of mixing can be positive, can deviate. It can be either positive or negative, and we have a factor here out front that describes that. And so if the net free energy change is negative, then our solution is going to be stable. And if the net free energy change is positive, our solution is going to be unstable and will unmix. So our entropy term, will always be negative, right? And it will reach a minima at a 50-50. That's where the greatest number of possible microstates are, the number of ways that the elements, the atoms of the individual elements can be arranged. If we have a negative enthalpy of mixing, we're going to have a stable solution across the whole range, right? We could have a positive enthalpy of mixing at a given temperature, but if the temperature is high enough, the negative component from the entropy term will dominate, and we can still have a low a negative delta G and still have a stable solution across the whole range. But what happens if we lower the temperature, right? Our entropy term becomes less negative. Our enthalpy term is still positive, so we can end up with a delta G of mixing where the enthalpy term dominates and we become positive, in which case this mixture will phase separate. So we want to look at what is going to happen in this situation, all right? What happens when we have an unstable solution, where we're not going to have a complete miscible solid solution strengthened alloy? So if we take a look at the plot of free energy as a function of composition, so here we have a negative delta G of mixing, so it's going to be negative all the way through. So here's what if I just did a tie line between the free energy of pure A and the free energy of pure B, we're always below that, right? And if we look at a particular composition, the delta G of mixing is given by the distance from the tie line down to the free energy curve, right? And we have to look at a couple different terms here, right? So the first one is the chemical potential, right? What does the chemical potential tell us? Well, remember, the chemical potential is the change in the internal energy of our system with infinitesimally small changes of composition, right? And so out here we have if we look at our definition, right? So it's the change in Gibbs free energy by changing the composition tiny way is equal to the chemical potential of each phase of element A in the phase times the differential in composition, right? So essentially what it tells us we can do is we can find the tangent line to the Gibbs free energy curve and extrapolate out to pure A and pure B And that gives us the chemical potential of species A in the mixture and the chemical potential of species B in the mixture. All right, and the chemical potential then we can define in terms of the Gibbs free energy of the component plus this term RT ln of AI. This AI is the activity of a species in the solution or the composition, right? It's a measure of the effective concentration. It tells you how active that species is compared to when it's under its standard state conditions, which is usually pure at atmospheric conditions is the way that's defined. So if we look at this, right, remember the natural log is a monotonically increasing function, right? At 0, it becomes infinite, right? So we can see here that the tangent line, right, if we have at the pure concentration has essentially infinite slope, right? But if we look at this, the greatest activity of B, well, it's going to be way over here when the tangents down here, right? But if this is stable and monotonic, what it tells us is the greatest activity is at super low concentrations, and the activity as we increase becomes closer to the pure state. Okay, so we have to look at the configurations that our solution can adopt. If we stay in solution, right, we can either be in a random solid solution, right, which means that the different species of A and B are randomly put on the lattice. So we can say that the probability of finding atom A on any given lattice site is going to be equal to the fraction of A in the overall solution. We can also have ordered phases, right, where we have a strong preferential site occupancy. For example, copper gold has complete miscibility, but they form an ordered structure by layers, right? So we have a much higher probability of finding gold and copper on different sites of the FCC lattice, right? So here we have the copper gold, and here we see the copper 3 gold, depending on the composition of the structure. Then we also have potentially intermediate phases where the minimum free energy structure is a different crystal structure, and it's typically in between the matrix and something else. And we'll talk about this with aluminum when we have intermediate phases of theta double prime and theta prime, which are in between the FCC aluminum matrix and the thermodynamic equilibrium theta phase, right? So this is the theta, and the theta double prime are in between. Okay, so if we have a heterogeneous system where we have more than one possible phase, right, we know that the free energy of the phase is going to depend on the composition, the temperature, the pressure, all of these, right? And at different compositions, different phases may have minimum free energy. So the question is, how do we determine the partitioning between these two phases? In this case, we have an alpha phase that's a potential and a beta phase that's a potential. Well, at low concentrations of B, we can clearly see that the alpha phase has a much lower free energy. And at low volume fractions of alpha, of A, we see that the beta phase has a minimum free energy. But what about when we're somewhere in the middle? If I'm at a point, say here, how do I determine how it's going to be partitioned into alpha and beta phases, right? And in which case, right, this is where we use our common tangent construction comes in. So we can imagine here we're at this composition G naught, right? And what if I partition my system into some of this alpha phase at this composition and alpha phase at this composition, right? I can see that I actually lower the free energy of my system, right? So that's a change that is potentially going to happen. But, all right, but how do I determine what's the global minima, right? I know if I'm in between, I can do this, right? It's just a simple energy balance, like the lever rule, right? So I want to find the partitioning that's going to maximize my change of free energy, right? And does it make sense that if I come down, right, from an energy point of view, we can see that this is going to definitely be maximized if I come down to the tangent between the common tangent between these two phases. Another way of looking at it is we can look at what's our condition for thermodynamic equilibrium. And that is that the chemical potential of species A has to be the same in both phases, alpha and beta. And the chemical potential of species B has to be the same in both phases, alpha and beta. Right? And the only way for that to occur is when we have this tangent, right? Because it means that the slope is the same, and if the slope's the same, it means the extrapolated intercepts are going to be the same, right? So this naturally leads to this common tangent construction, and it's a way of finding the minimum free energy for the partitioning of phases. So if we're at this G naught composition, right, X naught composition, we're naturally going to partition into beta of this composition, alpha of this composition, and beta of this composition. This is a typo in Porter and Easterling. That should be an alpha there. I didn't notice that before. Right? These two compositions. Right? And I'm sure in thermo you did the exercise where you looked at different parts of the phase diagram and looked at how we go from the free energy curves to the phase diagram. Right? And the important one is the eutectic, right? So at different temperatures, if I'm at the eutectic composition here, right, I'm clearly, I should make one more point, all right? So basically what this tells us here is if I'm in this region, this composition range, I'm going to be all alpha. If I'm in this composition range, I'm going to be in all beta. If I'm in between, I'm going to have a mixture of alpha and beta. Right? That should be self-evident, but I wanted to just reiterate it. So if we look at the free energy curves, if I'm at this eutectic composition, right, I'm liquid, I'm pure liquid, right? I'm in between the common tangent. So if I'm in this region, I'm alpha, liquid plus alpha, liquid, liquid plus beta, beta. I'm in this regime. Essentially, the eutectic point is where I have a common tangent across all three phases. This only happens at exactly one temperature, right? I need all 3 points to be all 3 points to be collinear. And if I follow that down, what it means is I stay liquid. This region, this liquid region, gets narrower and narrower as I lower the temperature. Eventually, I hit the eutectic point. So as I come down, I'm liquid, spontaneously freeze into alpha plus beta. Right? And you can do this for any phase diagram. Right? And so that is the common tangent construction, right? And this tells us the free energy of the individual phases, right? So it tells us what we expect thermodynamically to happen. What's the thermodynamic equilibrium, right? So given an infinite amount of time, right? But what it doesn't tell us is how hard these things are to actually nucleate and grow, right? There's no time in here. There's no difficulty, right? This is just a pure volumetric term, right? The phase is sort of in isolation, right? In real cases, we have to worry about the interfacial energy, right? How difficult is it? How likely are these two phases to want to be near each other, right? If the interfacial energy is low, we can have lots and lots and lots of small regions. If the interfacial energy is really high, the system will tend to minimize the interfacial component by nucleating and growing large particles that are well separated, right? We also have a lattice strain term because there's not the volume of these are not exactly the same. We have different lattice parameters. So that's going to give us a misfit strain that can either be, right, if our particle is denser than our matrix, right, we're going to have a tensile strain in the matrix, right? If it's larger, we're going to have a compressive elastic strain. So we need to take all of these into account to see if we're actually going to be able to nucleate our precipitation of our refined distribution, right? Because this is what we want, right? It doesn't do us any good to have one big chunk of something or really big coarse particles that are well separated, right? That's not going to contribute much to strengthening. So if we think about the total free energy change, we're going to have our Gibbs free energy change. We're going to have the volumetric, right? This is what we were talking about in our common tangent construction, which phases are thermodynamically likely to appear. We have a surface energy term, and we have a strain term. And notice that the surface energy term and the strain term have opposite signs to this, right? So if we look at it, we can rewrite this expression for the free energy change as a function of the particle radius, right, instead of volume, right? And that's a typo. That should be squared. Surface energy, surface term, surface energy is squared, not cubed, right? So our surface energy goes with the r squared. So this adds a positive component to the Gibbs free energy, right? So this is going to oppose nucleation, right? Our volume term is negative, right? Because in this case, we're trying to nucleate the thermodynamically stable phase, right? And our strain term is going to shift that over, right? And if we add the contribution of this line and this line, we have a curve that looks like this. So what it tells us is that nucleating small particles gives us an increase in the free energy. Big particle, because the surface, for these small particles, the surface energy term dominates. For big particles, the volumetric term dominates. Right? So that means if we look at the change in free energy, we have a maxima here at some radius r star. And we'll call this the critical radius. Right? So remember how this nucleates. This all nucleates by thermal fluctuations, by random atomic jumps. Right? So essentially we need to get a cluster of atoms that are the right composition that are a size r star or larger for this to become a stable nucleus. Right? If we're at the stable nucleus and it grows, we have a reduction in free energy. So that's naturally going to happen. There's a bias towards jumps that reduce our free energy. If we have a cluster a nucleus that forms that's less than r star, chances are over time it will go this way to reduce its free energy and go back to the phase, the parent phase. Right? So increasing our surface energy increases this activation energy, this delta G star, and activates the critical radius that we need. Right? So phases that don't fit well, that either have a poor interface or a poor volume match to our matrix, are going to be much harder to nucleate. Right? So two very important two very important points, right? So the precipitation of a very refined distribution of particles is going to be favored for transformations where the interfacial energy term is small and the misfit term is small. So we can imagine if we have an equilibrium phase with a very high strain interfacial energy or strain term, right, we can imagine that the activation barrier for nucleation is also going to be high. So it's possible to create a situation where maybe other metastable precipitates form. Metastable being that they are not the thermodynamically predicted phase at equilibrium. But they form in preference to the equilibrium phase because the surface energy and strain terms were small, even though their volumetric contribution was not quite as large. And this happens, the reason I'm bringing this up is because this is exactly what happens in the aluminum alloys that we're going to look at. Right? And so one last thing we have to look at is the nucleation rate. Right? So we have Arrhenius terms. This is the number of the nucleation rate, right? This is a factor. This is includes the vibration frequency and the area of the critical nucleus, right? Now we have two terms. One that is the activation energy, for nucleation, right? This is delta G star, so this is the activation barrier we have to overcome to create a nucleus of the critical radius, right? And then this here, this Arrhenius term, is the diffusion term, right? It's the activation energy for atomic migration. So if we look at this, here's our equilibrium, temperature, if we're very close to this equilibrium temperature, right, diffusion at a higher temperature, diffusion is easier, but we don't have a lot of driving force to overcome our activation barrier, right? We're really close to the equilibrium. As we cool down, this term grows, right? The farther away we get away from the equilibrium temperature, the larger the undercooling, the more driving force for this nucleation there is. But at the same time, at lower temperatures, the energy we have available for diffusion, our diffusion rates and our atomic migration rates decrease. Right? So if we look at the nucleation rate, we have a maxima at some undercooling, right? At higher temperatures than this, we're driving force limited. At temperatures below this, we're diffusion limited. Right? So there's an optimal undercooling to nucleate where the greatest number of nuclei are. Right? So what's going to happen if we only have a very small undercooling? Nucleation is hard, right? Because we don't have enough driving force for nucleation. But diffusion is easy. So that means we're going to nucleate a very small number of these, right? A very, very small number. And they're going to grow, each one is going to grow to be very large. Because growth is easy, because it's diffusional, but nucleation is hard. If we're down here below this minima, nucleation there's a huge driving force for nucleation. So we're going to nucleate lots and lots and lots of particles, but they're all going to grow to be very small because diffusion is limited. It might take a longer time also for nucleation to occur. Right? And just as a sort of a final case study, we'll look at this aluminum copper system, and that'll be covered in the other lectures. So again, that was just a thermodynamic review, looking at some of the key concepts. Right, the one idea. This is something we're going to use a lot. So the activation energy for nucleation and a critical radius for activation for nucleation is really an important concept. And the common tangent construction, how the phases are partitioned in heterogeneous systems. So these are concepts we'll keep coming back to again and again and again throughout the course. Okay, sorry that the recording crashed on the version that I gave in class. But at least I was able to do a sort of after recording and make it up so we have it. It'll be a little disjointed because the next bit will be a repeat from last year's lecture, so I don't have to record another hour and a half on aluminum alloys to make up for the missing stuff. Okay, thanks guys, and we'll see you in class.